Thank you for this opportunity. This is Professor Roger Hadgraft. I'm Deputy Dean Learning and Teaching at Central Queensland University in Australia in the School of Engineering and Technology. So I'm going to try to pull together a bunch of educational threads, and I've called it Reinventing Engineering Education. So I'm going to go through things pretty quickly, and hopefully there's some time at the end for some general questions. So many of you might have seen this picture before. It shows a lecture theatre in the Middle Ages, and it's the kind of thing that we kind of like to do. We like to talk at students, and it's been around for perhaps 600 years, or it might be longer. And if you took any of those, mostly gentlemen, and took them into a modern lecture theatre, they'd kind of recognise it immediately as a smarted up version of what they had back in those days. And this is what it looks now. So we've updated lecture theatres, but still it's a very similar kind of process. But what's new? Well, we've got things like Khan Academy, and we've got Code Academy, learn computer programming online. And of course, the big splash about 3 years ago were the MOOCs, started up by by the group at Stanford, who thought, well, teaching artificial intelligence to 150 students was kind of neat, but what if you could teach it to 150,000 students? How would that work? And many of you, I'm sure, have read many of the stories about how MOOCs have worked and not worked for many students. But nevertheless, it's a very powerful set of technology and a very powerful movement in higher education. So one of the companies that's spun out of that is Udacity, and I really like this quote that one of the students said, I think this is something as fundamentally new to education as the invention of printing. Those involved in distance education might disagree, but nevertheless, dealing with 100,000 plus students is kind of a pretty novel concept. So I'm going to list a bunch of problems, and I'm going to list a bunch of opportunities. And the first of these is the coming technological revolution that I think is going to have a profound effect on universities. And it's quite curious because potentially it's a race to zero. It's a race to delivering engineering education at zero cost. And if that's the case, well, what's the business model? What are we going to do? And yet, curiously, educational startups are one of the fastest growing entrepreneurial activities. So there are plenty of young companies that believe that they can carve out a chunk of the higher education and further education market and make good money out of it. So they're looking at low cost and large scale because, after all, we all teach a lot of the same things. Students learn statics and dynamics all over the world, and if you could teach that from one location and have 10 million students or 100 million students, you don't have to charge them very much to make a lot of money. So that's one challenge, the coming technological revolution. The next challenge is the fact that we're training students for a very challenging world. So we've got issues of sustainability, of energy, transport, communications, water, food, health, security. And many of you will have seen the National Academy of Engineering Grand Challenges, and I think there are 14 of them. And so we're trying to create these young people who are going to go off and transform the world, deal with these major changes in ways that were never talked about when most of us were at university. So that's problem number two, is we're educating students and graduates for dealing with a very complex world. Now, if you have a look at a lot of the international reviews of engineering education, so Robin King did a review in Australia, 2008, Sherry Shepherd and company produced a book called Educating Engineers Designing for the Future of the Field, which many of you will have read. The American Society of Civil Engineers produced their body of knowledge, a couple of versions, the Engineer of 2020 and so on. And there's a book recently published called A Whole New Engineer that talks about the transformations that have spun out of Olin College, and I'll come back to that a little bit later. So there are plenty of wise writings about this business. And what do they say? Well, what they say is that we need to engage students by getting a better balance of theory and practice, that most of our engineering programs have drifted towards the theory side with not enough practice. That there needs to be more industry involvement as part of that. There needs to be much more active learning. There needs to be sharing of best practice. And I guess your webinar series is a good example of sharing best practice. There needs to be more diversity in the student population, more women, more ethnic minorities, and there needs to be more hands-on activities. So you can see a picture of some students in a first-year class who had to design a deployable bridge for a disaster relief situation, and having a good time with that particular activity. So problem number 3 is we need to educate for professional practice. And that seems kind of obvious, but I'll explain why that's a bit more difficult than it looks. So what else is going on? So in our country, our federal government has created a new standards organisation for universities and further education. It's called the Tertiary Education Quality and Standards Agency. And they've set out and published a bunch of standards, and I'm sure this is happening in India as well, that governments, whether it's state or federal, are publishing standards and to raise the standard and assure the standard of all our higher education institutions. One of the projects that I was involved in that was allied to that particular exercise was what became known as the Academic Standards Project, and ALTC stands for the Australian Learning and Teaching Council, which is now called the Office for Learning and Teaching. And what they did was they funded 9 discipline clusters to look at what are the outcomes. So, and I understand that you've been talking about outcomes-based education in many recent webinars. What do those outcomes look like at the program level, at the degree level? And our work is then on this website, and we can make these slides available later. So disciplinestandards.pbworks.com. I was involved with Professor Ian Cameron from the University of Queensland, and we did the discipline cluster, which was engineering and ICT. Little snapshot of our website. Some similar work has been going on in Europe really since about the year 2000. It's called the Tuning Project, and if you Google that, you'll find a whole lot of very rich information that I'm sure will be useful to you. And then a third project which I was involved in was the OECD A Hello project, which was stands for the Assessment of Higher Education Learning Outcomes. And it was a feasibility project to investigate the possibility that we could set up a test for engineering competence that you could run in different parts of the world, in different languages, and get some sense of, how do engineers compare across the globe. And if you go to the OECD site, you can get the results of that study. So coming back to the work that Ian Cameron and I did, we produced what we called 5 threshold learning outcomes. So these are the 5 big ideas for both engineering and ICT professionals. And the first thing is that graduates need to be able to understand problems in context. And this includes issues of sustainability, for example. They need to understand problems in the business context as well. So it's all about problems and context, systems thinking. Then they need to bring to that problem some systematic problem-solving processes, and we usually call that the design process, or we might say, well, that's really what systems engineering is all about. And that is in turn supported by disciplinary knowledge. So whether you're a civil engineer or a mechanical engineer or an electronic engineer, you've got a kit bag of disciplinary knowledge that is special and useful to you. And then as an engineer, you'll almost inevitably work in teams. You have to communicate with other people, stakeholders, team members, and so on. And lastly, you need to understand, manage, and develop yourself. And if you look at these 5 big ideas, and I can send you the more detailed breakdown of them, and if you go to accreditation guidelines, and probably the best known of them are the ABET guidelines from the US, you'll see that these ideas summarize what ABET has documented, or what Engineers Australia has documented, for example. But what Ian and I really liked about these 5 ideas is they're relatively easy to remember, and they're pretty easy to explain to people, and when you do, they go, oh yes, I understand that. You can explain this to a parent who isn't an engineer, and they'll go, oh yeah, okay, yes, I can see how that works. Whereas if you start off with the much longer lists that ABET and Engineers Australia published, then you'll quickly lose people in the explanations. So, and the interesting thing about it is that when we compared our list from engineering and ICT with the health disciplines, with law and with accounting and so on, they were all surprisingly similar lists. So what it means is that across a university or across a college, most professions are doing the same kind of thing. Their graduates need to understand problems in context, they need problem-solving processes, they need disciplinary knowledge, they need teamwork, communication skills, and they need to be able to be reflective practitioners, basically, who can self-improve. So the other study that I want to tell you about was a project that I did with Professor David Dowling from the University of Southern Queensland, and it was called Define Your Discipline, and the project was focused on environmental engineering. And we basically asked a whole bunch of environmental engineers in many, many meetings. So we might have had 20 meetings with, say, 10 people in each meeting. And we simply gave them a block of sticky notes. And we said, write on each sticky note one thing that a graduate environmental engineer needs to do in your office. What do they do? Not what do they know, what do they do? And you can make that a big scale thing, a small scale thing. So you might say they need to write reports. They need to be able to go and collect water quality data. They need to be able to, I don't know, drive a truck. And then what we asked, people would normally spend 15 or 20 minutes writing ideas. And then we'd ask them to stand up and spread all the ideas out on a large table or on the wall, and we'd shuffle them into ideas, into categories. And what we expected when the project was designed is that the categories would look something like the top surface of this cube. And in case you can't read it, it says things like the technical categories of environmental engineering. So it would be things like water resources, stormwater management, water and wastewater treatment, soils and geology, waste management, air and noise, energy systems, sustainable communities. We thought they're the categories that they'd say, well, these are the sorts of problems that environmental engineers produce. But they didn't. What they consistently told us was these things on this vertical face of the cube. And after many of these meetings, we collapsed these down into 6 big ideas, and they were that environmental engineers, young environmental engineers, get involved in investigation, in design, in modelling, in assessment, so that's usually impact assessment, planning and management of problems, and audit and compliance issues, which is kind of interesting. And then if you look down here, on the bottom surface of the cube, there's this, what people often call generic skills, or in the UK they're called key skills, I think. So teamwork, self-management, information skills, innovation, communication, ethics, and project management. So, which is how we came up with the cube, is that we said, well, there's a set of problem skills which are transferable and useful on any particular kind of problem. There's a set of discipline skills, technical skills, which we tend to love to death and teach far too much of, and there's a set of generic skills. So there's a three-dimensional cube of skills that we're trying to teach our students, which probably explains why we all find it so difficult to design curricula to do all of those things in the space of something like a 4-year engineering program. So we've looked at what professional practice is, and in fact that's a conundrum for us, is that we're still trying to better understand what is professional practice. Yes, the accreditation authorities have tried to do that for us, but usually they haven't explained it very well. And there's quite a lot of research now going on in this area, and a recent book that was published by James Trevelyan from the University of Western Australia, The Making of an Expert Engineer, I commend to you to read, because I think for those of us who are academics and have been academics for a long time, it's easy to forget what it means to be an engineer, and it's good to be reminded. So that's an excellent book. Quite a big read, 612 pages. So what we really need to do is to rethink what a university education is, and so let's look at a couple of examples about what others are doing. Purdue University, which some of you know, has a School of Engineering Education and is one of the world's centres for engineering education research, had an initiative called the Engineer of 2020, and concluded that what the workforce needed was that graduates who were technically competent, broadly knowledgeable, adaptable and nimble. So the need for the Renaissance engineer. And remember, if you think back to that capability cube, those general purpose skills of investigation, design, modelling, impact assessment, management, so on, are the sorts of things that are transferable and operable across a 40-year career. And Olin College, which in Boston, which is one of my favourite examples, their mission is to prepare students to become innovators who recognise needs, design solutions and engage in creative enterprises for the good of the world. And again, I mentioned that book, A Whole New Engineer, which you can also download as a Kindle edition while I'm talking. Okay, so now what I want to do is talk about opportunities, and the first one is really project-oriented learning, and that's something that I've been involved in for about the last 25 years. To some extent, engineering programs have always had some project work. Unfortunately, too often it's been very late in the program, whereas what we really need is project work in every semester of the program. So if we think about projects and how it is that engineers do engineering, which is almost always in projects, and so building nifty spacecraft like this one, which was the one that intercepted the comet some months ago and dropped that probe, extraordinary piece of aerospace engineering. Well, how does that come about? How do engineers learn to do engineering? Well, the design process is pretty simple, and this is the simple version I tell my students, which starts with some kind of client need up at the top here. Basically what you do is you research the problem, explore the problem, try to understand the problem. You might have to go back to the client to help them to understand their problem. When you think that the problem is well defined, you move on to explore the alternative solutions, sometimes going back to research the problem. And then as the alternative solutions emerge, you move on to the evaluation phase, where what you're trying to do is to figure out which one is the best one. And to evaluate, you need some criteria, you need some requirements. And those really come out of the research phase. And I've listed them in a sustainability kind of way. So there needs to be social requirements, economic requirements, environmental requirements as a minimum, and clearly technical requirements. And then, of course, you might move to build and deliver and test and so on. So this process seems pretty simple. You know, you'd think, well, it'd be pretty easy to teach that to students, wouldn't it? And for those of you who are into systems engineering, you might be more familiar with the V diagram, which takes that simple diagram from the previous slide and turns it into something that's a little bit more rigorous, that demonstrates that testing should be happening from very early on in the development of in this case, the concept of operations. And I commend that book mentioned at the bottom of the slide there, Systems Engineering for Dummies, which sounds pretty flippant, but was produced by an expert at IBM, and it's actually available freely to download through John Wiley, no doubt sponsored by IBM. So how do you learn to do engineering as opposed to how do you learn fluid mechanics, for example? Well, you learn to do engineering through complex learning situations, and many of you will be familiar with Aalborg University in Denmark, which has been doing this since 1974, and my own university, which has been doing problem-based learning since 1998. And I think my original investigations when I was at Monash University in Melbourne started in 1991. So there's quite a lot of experience, and there are many other universities around the world who have, who are doing project-based learning to some degree. At both Aalborg and also at CQU, there is a sequence of project-based courses which represent 50% of the curriculum. So every semester, 50% of the curriculum is a project, and the other 50% are the supporting courses or subjects. So I thought I'd just quickly show you what our civil engineering program looks like. So here we are, the 8 semesters of the program. We've got these 2 project courses in first year called Engineering Skills 1 and Skills 2, where students develop a range of capabilities, not just engineering design, but it's learning teamwork skills, refreshing their communication skills, learning to become reflective practitioners. They learn some CAD and various other things. And alongside that, they're doing some mathematics and they're doing some engineering physics, and the second semester looks a little bit the same. And then in third year, we've got some general purpose design and management courses, which again project-based, and I happen to be involved in teaching this one at the moment. And this is where students start to formally learn project management and a deeper understanding of sustainability issues. You can see that they do a bit more mathematics. They start to do some, they're also doing some structures this semester. The next semester they're doing some materials and solid mechanics, and so on. So you can see that if you look up here to credit points, we've got 12 credit points here, and 6 credit points here, and 6 credit points there. So every semester is what we call 24 credit points. And a credit point is, well, no longer a very meaningful measure. Once upon a time, we imagined it was contact hours, but it's no longer contact hours each week. Okay, so that gives you an idea of how a program can be structured so that it's got a very significant project component with more traditional courses on the side. And the way I like to think about this is that students can be doing project work and also skill development. And the curriculum kind of divides those into two. So we say we do some project courses, we do some skill development courses. And in the skill development courses, that's where students are learning what I think is convergent learning and thinking. That is, they're learning to solve stress in a beam, or the safety factor of slope stability analysis, or something like that. In a project, they're learning to do divergent learning and thinking, so they're grappling with problems and trying to find solutions. And as the students get more experienced, so by the time they get to third year, then these two things can get blurred together. And in a one course, students are doing project work and then they're developing skills as they need it. So I've drawn this a bit like an infinity diagram, that they can go backwards and forwards from one thing into the other. And if you think about it in terms of Bloom's taxonomy, the lower half of Bloom's taxonomy, which is remember, understand and apply, but at the top is the high level analyze, evaluate and create. And they're really the elements of professional practice. And they're the graduate outcomes that require human input in the learning process, because they're sophisticated and they're nuanced and they need complex learning situations. Whereas the bottom half are enabling skills, and I've said there about 50% of most engineering curricula is of this kind. It could easily be replaced by technology. In fact, I think it's probably more like 75%. And I'll show you a sample curriculum in a moment that will illustrate that. Now, I've talked about the advantage of using technology, and we think that we have to keep putting students in rooms and talking at them to get them to learn. But if you look at something like lynda.com, here's a site where you can learn hundreds or thousands of things, particularly software packages, but a whole lot of business skills and so on. So the whole area of computer-assisted learning is just burgeoning and mushrooming, and soon I think much of what we currently teach in very old traditional ways, students will just learn online. Now, a while ago I went to the Apple App Store on my iPad and I searched for, in this case, engineering electrical, just to see what was available. And there are many, many packages already available. Structural engineering, here's something on mechanics. Here's some more sophisticated stuff on structural mechanics, fluid dynamics, vectors and so on. So there's a huge amount of computer-assisted learning material becoming available. And we could also be using, there's a whole range of sites spread around the world, many of which you will know, where you can download useful materials. So you have to ask yourself, why are we teaching in old traditional ways? And you probably also know about the CDIO movement, Conceive, Design, Implement, Operate, which is started out as a liaison between Swedish universities, I think it might have been KTH originally, and MIT in the US, and now has well over 100 institutions involved, including some from Australia and no doubt some from India. And this is probably the best organised movement around the world for for bringing universities together to work together to learn to teach better, and in that process to give students that project-based experience, so they can be doing the conceiving and the designing, but they're also doing the implementing and the operating. And you can see a couple of young people here building a small aircraft. And an essential part of all of this is going to be online assessment, because students need to be able to demonstrate their competence in easy ways, and we need them to be able to do that and not occupy huge amounts of our time marking exam papers. And there are pieces of software like PeerWise and others which are are being used for this purpose. So online assessment, a very important part of the future. At the moment we're engaged in a small shared resources project funded by the Council of Engineering Deans, and what we're doing as a startup is to start with assessment items. So rather than start with the teaching of something like statics, is to start with what do our exam questions look like? Why do they look like that? What do we think that we're assessing? And if we get together the 40-odd universities in Australia that teach engineering, it wouldn't be very difficult to build quite quickly a database of 1,000 exam questions that could be used for not just online assessment, but also for setting future exam papers. So if that's something that might be useful to you as a collective, then we need to think about how we could get involved and work together. Something you might be interested in is the Adaptive Mechanics Network, so adaptivemechanics.edu.au. This is work that's spun out of a couple of projects from at least 5 years ago now, and there's a company called Smart Sparrow that's now carrying this on and applying it not just in engineering but in other places. So I'll let you have a look at that in your own time. What's interesting about it is that it will test students' understanding of particular mechanics situations and then diagnose their misunderstanding and help them to better understand where they're not analysing the problem in the right kind of way. So opportunity number 2 is adaptive computer tutorials with assessment. Opportunity number 1, you'll remember, is project-based learning, project-oriented learning. And if we don't change the way we currently do things, then others will simply take away parts of our business. Now, I'm not sure what the pressures are in India, but I think sooner or later companies are going to realise that there's plenty of money to be made in higher education if we do it on a different scale. And Coursera is a good example of a company that's come out of this the MOOC era. Watch this space. So I thought I'd show you an example of the curriculum, and this is a mechanical engineering curriculum from a university I used to work at. And if you just skim your eyes over the different topics, particularly if you're a mechanical engineer, you'll recognise many of the topics. And what I started to do then was to shade in the topics that I thought would be relatively easy to teach with a computer if we had the resources to develop good interactive tutorials and online assessment. And I thought, well, you could actually teach a hell of a lot of first year, a fair bit of second year, a fair bit of third year, and most of fourth year. And as I said, somewhere between 50 and 75%, perhaps closer to 75%. So there's this technological revolution coming, and it can assist us by freeing up a lot of time that we now spend teaching things like statics and dynamics and circuit analysis to do the really interesting things, which is the project-based learning, the design subjects. So problem number 5 is how do we do curriculum redesign? And remember that opportunity 1 is project-oriented learning, and what we want to do is to have a curriculum where students swing from doing projects to doing skill development, during every week, perhaps every day. So I took that mechanical engineering curriculum, and I should own up and say I'm a civil engineer, not a mechanical engineer. And I started to group some of the courses together so that we had pairs which were a little bit more, one of them was more project-oriented, the other one is a bit more theory-oriented. So something like renewable energy systems is more of a project course, and I paired it with thermofluid mechanics, which is a theory subject. And what emerged out of that was that the mechanical program was really divided into about 4 themes. And the 4 themes look like this. There was a professional practice theme, there was a structures theme, a machines theme, and a thermofluids theme. And you could basically divide the year into those 4 themes. And any semester might have, perhaps 2 of those. And so I then combined some of those courses, and instead of having that multitude of courses that we saw before, I've now combined them into bigger units which now combine both practice and theory. And if we were a little bit bolder, we could have something that was even more interesting. So we could have green building design, electric vehicle design, and engineering for business, and so on. So there's ways of moving from the kind of very detail-oriented curricula that most of us have to a project-based curriculum. And what we're trying to do in those projects, or studios as the architects like to call them, we start with a set of professional capabilities, set of outcomes that we're trying to develop. We would have some supporting online modules combined with assessment to make sure that the students have learned the modules. We've got some sophisticated project studio work, which is usually group or team-based. And then at the end, we have some kind of exhibition, presentation, interview, and that's something that architecture schools do really well. And we have a portfolio that the students present. So if you do have a more traditional curriculum and you're trying to move in this direction, this is my six-step easy plan, that you need to create projects in more courses. So you can create a little project in even a traditional course if you just push some of the content aside. Not all the content needs to be taught. Then you start rethinking the sequences of the courses. You start to think, well, perhaps we should teach fluids 1, 2, and 3 slightly differently. You can identify project courses that run across the semester and share the projects across those semesters. You can combine courses into bigger units like I described before, and then eventually you can get to having multi- or transdisciplinary projects. So the solution is really project-oriented curricula with online support, online teaching, online assessment. I thought I'd give a bit of a plug for some work that we finished last year, which was good practice guidelines for curriculum supervision and assessment of final year engineering projects. I can make the link available so you can grab a copy of that, which is freely available. So really we're moving from teaching using traditional methods to personalised learning in the age of Google, because students will be able to progress at different rates. And a key ingredient will be they will need to assemble a portfolio. So we're going to have e-portfolio supported project-oriented learning. And if you think about how a gym works, I don't know how many of you have actually enrolled in the gym, but when you go to a gym, what they do is they start with a fitness assessment. So they might put you through a few tests and find out what you're capable of doing. They need to know what your plan is for, do you want to run a marathon, or do you want to just get a little bit fitter than you are now? And then they'll make up a plan of a weekly range of exercises. And our universities are moving in that direction. And that may not yet be very clear, but I think that's the inevitable direction that we're moving. So much more personalised learning where students can move at their own pace. So another small project that I'm involved in is this e-portfolio project, likewise funded by the Council of Engineering Deans to a small amount of money. We have Engineers Australia, the Australian Computer Society, and the Australian Council of Deans of ICT, who also providing support and encouragement. So that's an important project for us over the next year or so. So opportunity 3, personalised learning with e-portfolios. And this is my favourite quote really by Thomas Schul in 1986. He said, "The teacher's fundamental task is to get students to engage in learning activities," whereas we often think it's our fundamental task is to verbalize textbooks because surely students can't read. No, it's to engage students in learning activities. And sometimes those are very traditional learning activities, but more and more in the future they're going to be project-oriented activities. And we know it works. So here's a picture of a few of our students. They won a national competition last year for what was called The Big Idea. It was a project sponsored by a magazine called The Big Issue, which is a social activity for, it's a social publication to support the homeless. And they developed a pallet house, which is very interesting, a very cheap form of housing. So, summarising, what are our problems? We've got this technological revolution that is going to transform our jobs and our universities. We're training graduates to deal with very complex problems. And those complex problems are embedded in professional practice. The problem is we don't really understand professional practice very well, so we're doing some research about that. And we have old-fashioned curricula and old-fashioned teaching methods. When students want to be doing what you see in the picture, they want to be doing things. And yes, they need to learn the technical fundamentals, but they can do those two things simultaneously, not end to end. What we have as a set of solutions is project work, online tutorials, e-portfolios. We need to be able to redesign the curricula, and we kind of need to redesign ourselves and re-educate ourselves and hire new staff. And this picture shows students from RMIT in Melbourne, where I think they were runners-up in the Global Water Innovation Challenge, which was part of World Skills. So that was pretty brilliant that they were able to do that. So I'm going to stop there, and I'm happy to take any questions.
Did you have to get approval from external agencies to do the curriculum redesign?
No, although, of course, all of our programs are accredited. So universities in Australia are autonomous to the, and I understand some of the universities in India are as well. So that is, you know, in a sense, they set their own rules, but they are answerable to agencies beyond their walls. So, you know, they're answerable to Engineers Australia at accreditation every 5 years. They're also answerable to this new agency called the Tertiary Education Quality and Standards Agency. But both of those agencies are, you know, outcomes focused. So they're not about saying you must do it this way. What they're saying is, these are the outcomes we expect to see. You convince us that your curriculum is producing the outcomes that you've claimed. Are there any other questions?
Can you hear me?
Yes, yes.
Okay. How do you map new project-oriented courses with program outcomes for the course?
Well, in pretty much the same way that you map any course, any you know, every course, subject, unit, you know, in a program has a set of outcomes. Some of the courses, let's say fluid mechanics, will say have a fairly narrow range of outcomes. So in terms of Engineers Australia's framework, I think that's It's either 1.1 or 1.3, I think. 1.3, I think, is deepening technical knowledge in the discipline. So let's say fluid mechanics fits in there, and we can say, well, almost all of the hours taught teaching fluid mechanics is devoted to deepening that technical knowledge that I talked about. Project courses are much more complex because students are not just learning a technical capability, they're learning a whole suite of professional outcomes. So they're probably learning to do design. They're also learning to use certain design tools, so they might be using specialised software. They're exercising their project management skills. They're working in teams. They're communicating, in written form, in oral form, in graphical form. They might be grappling with issues like ethics related to sustainability. They're practicing innovation and so on. And so, you've really got to tease out what are all those individual outcomes. Now, for our project courses at Central Queensland Uni, we specify each of those things as learning outcomes. And what the students do in their semester portfolio is that they have to demonstrate to us that they've achieved that learning outcome. So we design the learning activities to deliver each of the outcomes, but it's up to them to then convince us that yes, they have been paying attention, and that that they've developed and show evidence of each of those things. So things like teamwork, for example. If it only relies on the academic to assess teamwork, then you tend to get a fairly narrow view of what the student knows about teamwork. But if instead you ask the student to write reflectively about teamwork through the semester, to keep a diary, then at the end of the semester the students can usually write very profound and meaningful things about what they've learned about teamwork through their interactions with their peers. So when you shift the assessment, when the assessment activity is shared between academics and students, much richer assessment data is collected. And then that gets mapped into the kind of accreditation documents that we present to Engineers Australia to say, well, this is how all of our technical and professional outcomes are being achieved through these project courses, but also through the traditional technical courses.
How often do you redesign your curricula?
Yes, that's a good question. I'd have to say that major redesign happens fairly infrequently. So, in fact, that's exactly what we're doing at Central Queensland Uni at the moment. And it's more than 15 years since the last redesign. But in that time, the program hasn't stood still, and there have been, small changes, but over that 17-year period, the structure has remained much the same. But this time, we're going to change the structure a bit, and pull some of the. We're pulling some of the traditional teaching into first and second year, pushing some of the project work into third and fourth year, because we have a co-op program where students go out on 2 6-month work placements, and they do the first one after second year. And we just felt that the way the program was operating, they didn't feel confident they had the full set of technical skills when they went out on their work placement. So we've downsized the project work a little in first and second year, boosted the amount of traditional learning, but what that's allowed us to do is to increase the amount of project work in third and fourth year. Yeah, so, let's say every 10 to 15 years, but, I don't know, barely a year goes by when somebody doesn't want to change something inside the program.
Can anyone join peerwise?
They can. It's operated out of the University of Auckland, and if you just go to their website, you can sign up. You sign up as an academic, and you get special privileges. You can set up a class. So it's very, very easy. The essence of peerwise is that students write the questions. So you might want to Google some of the publications that come out of peerwise. I used it for a couple of semesters, and I've had other colleagues who've used it. You have to give students incentives to write questions, and it's interesting to see the questions that they write. And most of those questions are used for revision and for just basically testing themselves. And it's quite helpful for students to see the questions that other students write, because it's a way of them getting a sense of, well, am I understanding this the way others do?
You mentioned that 75% of engineering curriculum can be replaced by technology. Can you please elaborate?
Well, if I go back to that slide, which is this one. Okay, if you think of engineering mathematics, engineering mechanics, manufacturing systems, engineering mathematics, blah 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 blah, a lot of those traditional courses are just, here's a bit of knowledge, here's a problem that you should be able to do now. Let me test you to see if you understand that. And gradually we're getting better and better computer tutorial systems. It's only a matter of time before a lot of engineering topics will be taught and learned online. And already students learn a lot of this not by sitting in our lectures. They learn it by Googling and downloading material from other places, watching YouTube videos. One of the slides I cut out for this evening was there's a website in Australia, and it might be all over the world, called Spoonfeed Me. And with Spoonfeed Me, students who've done a course upload their lecture notes and probably assignments. And so students are just have access to so much information and knowledge now that why do we sit them in lecture theatres to get this information and knowledge when they just pick it up for themselves? And that's why we need to rethink how we spend our time. We're all time poor, we're all being asked to do more research. What we need to do is to make students our allies and stop them being dependent on us and become much more independent learners, and that's what they learn by doing projects.
How much time did it take to stabilize the project-based oriented curriculum for each semester?
Well, here we are. At CTU, it's about year 17, and we're all still arguing about it. So in a sense, every semester, although we know what we're doing, we're constantly fine-tuning and rethinking, and of course our student population is constantly changing. So, and that's an interesting thing, and we choose different projects every semester, so every project has to be thought about in terms of how we're going to go about it. So will you ever stabilise it to the point where you don't have to think about it? No, you won't, and I don't think you want to either. I think what you want is a really interesting and dynamic work environment and learning environment for both students and staff. But certainly, for those who are interested, we could help you to get started in this kind of learning. because we do have a lot of experience spread across our academic staff.
Are there any specialized training centers to re-educate the engineering teaching staff?
There is. Aalborg University operate a Master of Problem-Based Learning. So, for those who really want some formal learning, then that would be a great place to start. There are other specialised courses. I know Michael Prince at Bucknell University in the US. He operates a course. I think it only runs once a year, and I've invited him out to Australia, but I haven't been able to convince him yet. But there are experts around the world who can come and run a 2 or 3 day or 5 day short course where a sort of total immersion. But to be fair, most engineering academics have some project-based learning experience. They've supervised PhD students. They've supervised usually final year project students. They kind of know what projects look like. Now, you can't run projects in first year the same way you can run them in final year. But it's not such a scary thing, and I'd be happy to provide assistance and further direction for those who are interested.
In terms of finances, how do you feel problem-based learning will match the current practices?
Well, I believe that problem-based learning is no more expensive than current practices. Certainly the way the medical schools adopted it, they used a fairly expensive model that none of us can afford. But, in all my teaching, I've only ever used the same number of teaching hours that anybody else has. My job, though, is to get the students to the point where they can learn for themselves. So rather than think that, if you've got 150 students studying your course, that you have to answer every question they have, your job is to really help them to learn to answer each other's questions. And I think most uni students figure this out pretty quickly, that if they don't develop study groups, then, they don't have that assistance from other students. And PBL just plays into that it makes it easy for students. Students are already working in teams. They're already studying alongside other students. So it becomes more and more effective, and you get brilliant work like those examples I was showing you of student groups who've done project work where they've won national and international competitions.
May we have some best practices in evaluating project outcomes, especially relative to intra-group and intergroup?
Yes, there are plenty of good practices, though I couldn't possibly summarise in a few words. A couple of people who've done really good work in that area have been Keith Willey and Anne Gardner at the University of Technology in Sydney. So they're using a piece of software called Spark, which I think stands for Self-and-Peer Assessment of something. So they've got a lot of experience in students and academics evaluating programs. And I can easily put anyone who's interested in touch with them. A quick Google will find them, though.
Regarding the peer-wise, the same professor asks, I'm from India and the website doesn't show any Indian universities.
Well, there's always a chance to be first. Yeah, I don't know why there are no Indian universities yet, but yeah, just leap in and have a go. It's very easy to to get started.
And the last question, what should the typical number of credits for project-based learning in each semester be?
Well, I don't know how you count credits, but in our case it's half the credits of the semester. So 50% of our semester is a project course, and the other 50% are more traditional technical courses. However, there are some universities where that amount of project work is 25%. So, you know, anything from 25 to 50% is a good arrangement, where it means that every semester the students are actually learning to be engineers. They're actually doing engineering. They're doing it through project work, and at the same time they're also sharpening up their technical skills.
Those are all the questions. Thank you very much, Dr. Hadgraft.
You're most welcome. Thanks for the opportunity.
I'll send you the recording by tomorrow.
Okay, thanks.